Okay. And here are responses. Okay. Oh, they disappeared. Where are they? Oh, there you go. Okay. So most of us said the bonding electrons will spend more time around fluorine. Okay, that's perfect. Okay. Why? Fluorine has a higher electronegativity than carbon, meaning the bonding electrons are going to spend more time around that atom. Okay. And then the bonding electrons will no, let's go with E now. The second most popular answer. The electrons in the valence shell of fluorine have a lower potential energy than the electrons in the valence shell of carbon. And that is correct as well. Why? Lila, go ahead. Oh, Lila, can I give the chance to Alexis? I'm going to come back to your question. Alexis, I saw your hand too. Is that right? Alexis, why do you expect the potential energy in the valence shell of fluorine to be lower than that of carbon?
Well, fluorine also just has more like valence electrons in the outermost shell. So obviously, when we're looking at potential energy, the valence electrons in the carbon atom would be more attractive, like, and would have higher potential energy than S since they'd be more distributed. I don't know if that reasoning makes sense.
Yeah, so I think you're hitting the right words, but we can boil it, we can summarize it a little bit more, yeah? So what we can do, you already said that. We have strong attraction towards the electrons
Yeah.
in fluorine. Okay, and the mantra is stronger the attractive interactions, the potential energy what?
It's lower.
Lower the potential energy. That's it.
I'm just going to say the electrons were closer to the.
Closer, yeah, closer, yeah, because of the strong attractions, right? Remember the mantra again, the potential energy is all about the attractive interaction strength. The stronger the attractive interactions, the lower the potential energy, okay? So if the electrons spend more time around fluorine due to attractions, therefore it should have a lower potential energy, okay? And then that's it. And then these are the only two correct answers there. All right. What questions, concerns, comments? Oh, one other thing I want to mention. So, how do we know which atom gets the negative charge and the positive charge? Okay. So, one more time, more electronegative means electrons are going to spend more time around that atom, meaning you have a higher electron density, meaning partial negative charge. Okay, the other side should be partially positive. That is it. Higher electronegativity means the partial negative charge will be, around that atom. That's it. Yeah. Any questions, Laila? So you give me a second. I'm pretty sure we can do something like that. So you're talking about like something like this. So now remember, it's just not say it's going to be a complete molecule, right? Something like that. Okay. So the idea is this. The most electronegative atom here is fluorine, therefore it has to be negative. Okay. Compared to that, the carbon should have a partial positive charge. But so if you compare hydrogen, compared to hydrogen, carbon is more electronegative, therefore you should get the partial negative charge compared to hydrogen. Okay. So is that your point? Is that getting a little bit more complicated there? Is positive because fluorine determines that. The most electronegative atom is the key. You start from there. If that is negative, whatever the atom bonded to that must be partially positive. Yeah, we don't even care about that. So you're going to see that today, anything with only carbon and hydrogen are considered as non-polar. Any carbon hydrogen, anything with carbon hydrogen are considered non-polar for all our purposes. We can talk about that towards the end of today. All right, we'll do more of those today, but the main thing I want to do today is to think about molecular polarity. Okay, so I'm going to switch to my notebook for a second. I hope that we will take this seriously and understand this right away. That's going to be my goal. So all this time we talked about the bond polarity. Now, when we switch to molecular polarity, okay, so let me write that. Molecular polarity or net dipole moment. I'm going to call this mu sub net for net dipole moment. Okay. So the idea is when you add the bond dipole moments, or if you sum the bond dipole moments, okay, you're going to get the net dipole moment, and that determines the molecular polarity. Let me write this out too. Okay. This is going to be the sum of bond dipole moments. That's all we need to do to determine whether the molecule is overall polar or non-polar. That's it. We add up the bond dipole moments. Let me show you an example. Let's take carbon dioxide. Okay. So here's carbon dioxide. Okay. We know in carbon dioxide, out of carbon and oxygen, oxygen is more electronegative. Therefore, it's going to get the partial negative charge. Carbon will be partially positive. Oxygen will be partially negative. Okay, these are the partial charges of them. And then if we drew the bond dipole moments, we're going to have one going in this direction. We have another one going in the opposite direction with the same magnitude. Okay. And therefore, the net dipole moment is this vector, this bond dipole moment vector added to this bond dipole moment vector. Okay. So we are adding two dipole moment vectors which are equal in magnitude but opposite in direction. What is going to happen if we add them up? Yeah, it's going to add up to 0. Thank you. Okay. It's going to add up to 0. Okay. So mu net or net dipole moment is 0, meaning our molecule is non-polar. That's it. So you can see that we have highly polar bonds in carbon dioxide, but the overall molecule is non-polar. Why? The net dipole moment, or when you add up the bond dipole moments, they add up to 0. Therefore, the overall molecule is non-polar. Okay, what questions, concerns, comments do we have at this point? Anything? Any questions, concerns, comments? Paul, do we have a question? I felt like you had a question. Something else. Okay, yeah, I'll come to you. Alana, did you have a question? No? Okay. All right. So, this is all we're going to do. Now, there's another thing maybe I should mention right away. So we're going to have a little bit more complicated molecules after this, right? So we're going to have trigonal planar and then all those stuff. So, you know what? I think it's best you do it. Can you draw SO3, okay, molecule on your whiteboard? Draw the hybrid structure. I know it has resonance, okay? Draw the hybrid structure of SO3 and determine whether this molecule is polar or non-polar. Go ahead. We forgot. We drew SO3 structure, the Lewis structure the other day, okay? We noticed that when we do the structure, we can have like 3 options for the sulfur to have octet, meaning we can draw 3 different Lewis structures, meaning it has resonance. Therefore, the hybrid structure should be in between, like a hybrid of all these, meaning each bond is a bond between a single and a double bond. It's not a double bond like this. It's not a single bond like these two. It's going to be in between. And that's why we have a solid line and a dashed line. And our hybrid structure looks something like that. Okay. So anyway, what did you say? Is SO3 polar or non-polar? Let's take a vote. Okay. Who says SO3 is polar? Anybody SO3 polar? Okay, I have a few hands. Who says SO3 is non-polar? Isaac, I did not see your hand going up at all. Is there a third option that I don't know about? Okay, okay. All right. So now, thank you. Now let's see what's going on here. All you have to do is to draw the bond dipole moments. Okay. So here's my SO3. Okay. And then what I'm going to do is I'm going to draw the bond dipole moments. Before that, I know my oxygen is more electronegative than sulfur. Therefore, oxygen must be partially negative. Okay, all my oxygens will be partially negative. My sulfur must be partially positive. That's something I would do to begin with. And then I'm going to draw my bond dipole moments. So we should go from positive atom to the negative atom. Here's one. Okay. Here's two. And here's three. Now, there's a trick that we can use to, at the bond dipole moments, or any vectors for that matter, that is to arrange these vectors head to tail. This is called the head to tail method. So here's one vector. You can pick any vectors. It doesn't, that order doesn't matter. Okay? I'm going to arrange the other vector head to tail from that. So here's head of the first vector touching the tail of the other one. And then here's the last one, head touching the tail of the other one. Okay. Yeah. You see that when I did that, I came back to the origin. Okay. So let me have a different color. Okay. I started over here. I came back to the origin, right? I came back to the same place. Therefore, so if there were displacement, what is my net displacement? It's zero, right? So if I came back to the origin, okay, my net displacement is zero. Okay, so just like displacement is a vector, the dipole moment is a vector as well. If you come back to the origin when you arrange them head to tail, your net dipole moment is going to be zero. Right? So your mu net, or the net dipole moment, mu net is zero. Therefore, SO3 is a non-polar molecule. Okay. What questions, concerns, comments do we have at this moment? Okay. Now we are not. Do you have a question, sir? Can I have the microphone there, please? Who has the microphone? Nathan?
So for the CO2, there's only two vectors. Wouldn't there be displacement then? As we said, it was non-polar.
Yeah.
But if you like did the head to toe, it wouldn't go back to the origin. That's what I'm wondering. Use that.
Okay. Okay. So one more time, please pay attention now. The question is about CO2. I think I was told that it should not come back to the origin. Let me see if that's the case. Let me see. Okay. So here's CO2. I'm going to draw the bond dipole moments. Here's carbon. Oops. Here's carbon to oxygen, and then carbon to oxygen. Okay. I'm going to arrange them head to tail. Here's one. And if I arrange the other one head to tail, so head to tail, I started over here and then came back to the same position. Right? Yeah, same thing. So again, remember, dipole moment is just like displacement is a vector, dipole moment is a vector, right? So if I stood here and if I took 5 steps this way, like 1, 2, 3, 4, 5, and I turned around the opposite way and then took another 5 steps, 1, 2, 3, 4, 5, what's my net displacement? 0, right? Same idea goes there. Yeah? All right. Any other questions, concerns, comments? Isaac. Nathan, can I have the microphone here?
So like in this example, the magnitude is important, right? Like we have to make, like if we want to assume that it's non-polar, we have to assume the bonds have the same magnitude, right?
Yeah. I mean, we're not going to assume. So if that same bond, they have the same magnitude. Yeah. Yeah. And then also, when you're determining the net dipole moment, because we do not know the values of the bond dipole moments, we cannot determine the value. Okay. We can only determine the direction of the net dipole moment. That's all we can do. All right. Now, I mean, I'm talking about the net dipole moment, but we haven't seen any molecule with any net dipole moments yet, right? Can you draw water molecule, H2O, and determine whether it is polar or non-polar? If it is polar, I want to see the net dipole moment of the molecule drawn over it as well. Go ahead. For this, okay? So we have H2O And if you draw the molecule, we have oxygen in the middle. To that, we have learning assistants. You got to bear with me for a minute here, okay? So don't shout at me yet. Okay. So yeah, so I saw this structure, okay, and then you indicated that we have only 4 electrons around oxygen now, so we need 2 lone pairs, which is pretty good. This is good Lewis structure. I will accept that for a good Lewis structure, okay? And then you went ahead and drew the bond dipole moments. They were fine as well. We are going from the positive atom to the negative atom. So here's one going this way, okay? The other one is going in the opposite direction, but it has the same magnitude, like this, right? And then we see that if we add them up, so we have one going this way, added to the other one going this way. If you add them up, what's going to happen? It's going to add up to 0, right? Okay, that's 0. Therefore, it should be non-polar. Okay. What's happening here? Are we okay with this? Why not? What's wrong with this? Thank you. The geometry of the molecule. Remember, there's a reason why we talked about the molecular geometry before we started talking about the molecular polarity, right? So this is wrong. Let me tell you why this is wrong. The geometry determines everything, okay? So actual molecule is not linear, it is bent. Why it is bent? Because we have a tetrahedral electron domain geometry around the oxygen atom, like this. Okay. Now, if I drew the bond dipole moments again, okay, here's 1, and then here's 2. Okay, let me call them 1 and 2 so that you know what I'm doing. 1, this is 2. Okay. So now if I do the net dipole moment, I'm gonna redraw 1. Okay, so I'm gonna have the same direction and the magnitude. So it goes like this. This is my 1, and this is my 2. 2. I see that I started over here and I ended up over here. Okay, so I have a net displacement or net. This is not displacement. This is dipole moment. I have a net dipole moment going from my starting point over here to my end point over here. Okay, so this molecule has a net dipole moment, or mu net is not 0. Therefore, this is going to be a polar molecule. Okay, this is a polar molecule. And then remember that if you did not draw the molecule to the correct geometry, you would have gotten the opposite answer, which is exact, which is wrong. Okay, so it is important that you draw the molecule to the correct geometry for you to get the correct answer. Okay, now if I draw the same dipole moment vector, you're going to see this in exams as well. You might see that the net dipole moments are drawn like this over the molecule. Okay, so we only care about the direction. So in the net dipole moment, the arrowhead is going towards the more electronegative atoms. Okay, and the arrow tail is in between the two less electronegative atoms or partial positive atoms. All right, I wanted to pick the red pen, but black one, I'm sorry. Okay? So we have two, let me draw the partial charges as well. My oxygen is partially negative because that's my more electronegative atom. These guys are partially positive. Number 1. Okay. Then I draw the bond dipole moments. I have one going this way, the other one going this way.
Yes.
Now I'm going to take these vectors. Here's one. I mean, we can pick, order doesn't matter. We can pick any vectors here. Okay. Let's pick this one. Here's my 1. I took one of them out, and then I'm going to arrange the other one head to tail. So head of the first one kissing the tail of the next one.
Okay.
So I see that it arranged like that. So I see I started over here and ended up over here. So therefore, I haven't come back to the zero, the origin, meaning my net dipole moment is not zero. My net dipole moment is going from here to here. Okay, so that is my net dipole moment. If I just draw it over the molecule, it's gonna be like that. All right, that's one. That's the second way. Now I'll do another way, Ronaldo. Okay, let's think about this as a displacement. Okay, so I stand here. Okay, I go 5 steps this way. 1, 2, 3, 4, 5. I turn this way and go 5 steps. 1, 2, 3, 4, 5. What is my net displacement? From there to here. Yes?
Right, it'd be 10 steps just away from,
Come again?
it's 10 steps away from the,
Yeah, it's not exactly 10 steps away. We need to use something else to
Right.
do that. But I was there before. Now I'm here. So if I draw a line from there to here, that is my net displacement.
right,
That's exactly what is going on there as well.
okay,
Yeah?
okay,
We'll do more examples and then, we'll come up with that.
okay.
Yeah.
Thank you.
All right. Any other questions, concerns, comments at this point? Isaac, how are we doing on that? Do you understand what's going on? Any questions?
No.
Do you have a question? Come that again?
Yeah, no.
We don't care about the vector. It's not a vector calculus or anything like that, okay? So do you understand how we determine that as a net dipole moment? That's all that matters. I will not ask what a vector is in the exam. So if you don't know, you will still get 100% on the exam. Okay. Any other questions? So by the way, just for information, vector is something that has a magnitude as well as a direction. That's it. Any other questions, concerns, comments at this point?
No.
Okay. So
Yeah, there's more large items.
let's do this.
Why it's 6 times.
All right. I believe this is NO2.
There's 4.
All right. Can you determine whether this molecule is polar or non-polar? Okay. And if it is polar, I want you to draw the net dipole moment of the molecule. Go ahead. NO2.
Now is.
Oh,
Then you can.
all right. So let's see. Let's take a vote one more time. All right. Can I have your attention, please, everybody? I need your attention now, okay? All right. First of all, who says this molecule NO2 is non-polar? Nobody. Who says NO2 is polar? Thank you. Yeah, it is polar. And then can I see your whiteboards for the dipole moment, the net dipole moment? Did you draw it? It's it. Very good. Okay. Can I see the other ones? You're working on that? Lillian? Okay. All right. So did you draw the dipole? Okay. Okay, yeah, you got it. I checked a few ones. Okay. The people who draw the dipole moments, they got them right. Okay. So anyway, here's what we have. We have nitrogen is partial compared to nitrogen, oxygen is more electronegative. Therefore, oxygen is going to be partially negative. And then my nitrogen would be partially positive. Okay. So if I drew the bond dipole moments, I have one going this way, another one going this way. If I arrange them head to tail, here's one. Okay. Here's two. They do not complete a shape. That means my net dipole moment is not zero. If I drew the net dipole moment, I started here. I ended up here. Therefore, my net dipole moment has this direction. Okay. If I draw it on the molecule, it should be like this. Okay. That would be my net dipole moment. Who said CF4 is non-polar? Okay. Yeah, it is non-polar. Okay, I'll show you why. And also I want to point out something else, what you know, that you drew on your whiteboards, most of us, but that's okay. Now, here are my bond dipole moments. Let me actually draw the partial charges. Fluorine is more negative than carbon, therefore fluorine has a partial negative charge compared to carbon, right? To indicate that, right? So my carbon is partially positive. And then if I drew the bond dipole moments, I have one going this way, another one going this way, another one going this way, another one going this way. If I arrange them head to tail, okay, in any order, so I can pick anything. I'm gonna pick, I don't know, let's pick this one, okay? Here's one, oh, and here's two, head to tail, and then here's three, head to tail, and then here's my fourth one, head to tail, okay? It came back to the origin, therefore my net displacement or net dipole moment is zero. New net is zero, okay? That's why this is non-polar. Okay? Now, I know that you could have gotten to the same answer if you drew a square planar molecule, okay? But you got lucky that there, okay? So this is a 3D molecule. It's really kind of hard to draw this head to tail method in the 3D molecules, but it should work something like this, not as in a square planar molecule. So it's not a square planar molecule. You need to know it's a tetrahedral molecule with a 109-degree angle between the bonds rather than 90-degree angle as in a square planar molecule. Okay. All right. What questions, concerns, comments do we have at this moment? One other thing I want to mention, as soon as you replace any one of these fluorines with something else, it's going to become a polar molecule. So if you have any tetrahedral, you have to make a note here so that you won't forget this. If you have any tetrahedral molecule with the same four atoms, same four bonds, then it's a non-polar molecule. Like in this case, we have carbon with 4 fluorine, it's a non-polar molecule. Carbon with 4 chlorines is a non-polar molecule. Carbon with, say, 4 hydrogens in a tetrahedral molecule is a non-polar molecule. However, as soon as you replace one of these, or 2 of them, or 3 of them, okay, with any other atom, it's going to become a polar molecule. I'll show you an example really quickly, okay? So I'm going to replace one of these fluorines with hydrogen. Here's that molecule. This is CHF3. Now, if I drew the bond dipole moments, let's do the bond dipole moments for the sake of time, okay? So because fluorine is more negative, so I'm gonna have one going this way, another one going this way, another one going back, another one coming from hydrogen to carbon like that, okay? Now, if I arrange them head to tail, okay? So I can pick, I can start from anywhere. Let's start from here. Here's 1, and then here's 2, and then here's 3, and then here's 4. It did not come back to the origin, okay? I started over here. This is my starting point. I ended up over here. Therefore, my net dipole moment should be in this direction. This shows me the direction of the net dipole moment. If I drew it on the molecule, it should go like that. Okay. Another way to think of this is my arrowhead, which is the partial negative part of the net dipole moment, are in between the partially negative atoms. Do you see that my partial negative atoms are over here? My arrowhead is exactly in between them, and my arrow tail is by the partial positive atoms over here. Lila?
I know this cannot happen, but if one of the fluorine bonds turned into a double bond, would it also become polar?
One of the fluorines?
Yeah, one of the fluorines turned into a double bond fluorine. Would it be polar?
So here's the thing. I mean, if it's a double bond, it's not going to be tetrahedral anymore. It's going to be like a trigonal planar geometry, right? Okay, hypothetically speaking. So if it is hypothetically speaking, if it is like 3 fluorines bonded to it, then it's going to be a non-polar molecule again. Yeah. So because if one can be double bonded, the others can be double bonded too, meaning you can have resonance and stuff like that, hypothetically speaking. So therefore it's going to be a perfectly symmetrical trigonal planar molecule, just like SO3. Yeah. So it's going to be non-polar. All right. What other questions, concerns, comments do we have at this moment? Right. So let's have some fun with 3 more molecules. Let's do it like this. Here we go. Nathan. Okay. People who draw the molecules or try to draw the molecules are, having an easier time dealing with these questions. People who try to like imagine the dipole moments in their head without drawing the molecules, they are the people who are struggling. Okay. So again, the take-home message is draw the molecule. I won't add another word in between them, but anyway, it doesn't matter. Draw the molecule. Okay, that's gonna be really helpful. So SiCl4, silicon and carbon are in the same group, therefore should be similar. Okay, so because carbon, I'm sorry, I need to have different color. Okay, so we know if this was carbon, it's going to look like this: Cl, and it's a tetrahedral geometry, Cl and Cl. And then all I did was I replaced my carbon with silicon. They bond the same way because they're in the same group. Okay. And when it comes to CS2, the same thing. Okay. So we know carbon dioxide is like this: oxygen, oxygen. Okay. Oh, that was a crooked oxygen. That's okay. Oxygen. Now what I'm going to do is oxygen and sulfur are in the same group. So I'm going to replace my oxygens with sulfur. I can do this because they are the same group elements bond the same way. Sulfur and sulfur. Okay. And then SCl2, sulfur in the middle. Then we have Cl and Cl. Okay. And then to have an octet around sulfur, we know we only have four electrons around it because from the 2 bonds, I need to add 2 lone pairs. Okay. So therefore it's going to have a bent geometry like this. And then even here, and it's not a bad idea to make sure that you draw the Lewis structures, as a practice. Okay. So they should all have 8 electrons around. So these are my molecules. Okay. Same thing over here. 8 electrons. Octet is the king or the holy grail of Lewis structure. Okay. Now we know that tetrahedral molecules like these are going to be non-polar. Okay, mu net is 0. Okay, therefore they are non-polar. Okay, just like carbon dioxide was non-polar, CS2 must be non-polar. Okay, and on the other hand, carbon and sulfur has similar electronegativity values. Okay, but sulfur is slightly more electronegative. Either way, they cancel each other out, right? So if you draw like this, they're going to cancel each other out. Therefore, they're going to be non-polar. On the other hand, if you take SCl2, chlorine is more negative than sulfur. Therefore, you're going to have 2 bond dipole moments going towards chlorine like this. Okay. Therefore, in my net dipole moment, I'm going to skip the head to tail now. Okay. Let me show you my thinking. I know that my arrowhead must be in between the 2 chlorine atoms. Why? My chlorines are partially negative. My arrowhead is partially negative. Therefore, my arrowhead of the net dipole moment must be here. My arrow tail must be converging on sulfur because I see my arrow tails for the bond dipole moments are converging on sulfur. Therefore, I would draw the arrow tail over here. This should be my net dipole moment. But if you do the head to tail method, here's my 1, here's my 2, randomly, one can be anything. So I draw 1, same direction. I draw 2, head to tail, head kissing the tail of 2. Okay. And then if I draw the net dipole moment, I started over here and I ended up over here. So I can see again, the direction of the net dipole moment is going down. I just do the same thing on over the molecule. So that's my polar molecule. Okay. This is not hard. This is easy, but there's a slight learning curve. You just need to go through that. You need to draw the molecules, draw the bond dipole moments, and then do the first work. After that, it's going to be much easier. It's like playing the piano. Right? All right. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Any questions? No? No? Are we good? Are we okay? Yeah, we understanding this. Ronaldo, how are we doing? We're getting there? We need some practice. That's it. Yeah, yeah. It always like that. Leo, how are we doing on this? Make sense? Yeah? Wonderful. Wonderful. Any questions at this point? I think we are getting there. Okay? So that is that. Let's do this. Now, notice that we have like 3D molecules. It's kind of hard to draw the head to tail method, right? So instead of always drawing head to tail, like for the bond dipole moments, we can just look at the symmetry of the molecule or symmetrical distribution of the charges. Okay, here's an example. If you take a tetrahedral molecule, okay, if the electronegative atoms are distributed like evenly, like this, like in CCl4, CF4, CH4, CBr4, then they are going to be non-polar, okay, because of the symmetric distribution of the charges. If you have a molecule like, say, hexafluorobenzene, again, because of the symmetry, a symmetric distribution of the charges, is going to be non-polar, just to make sense of that. So here's one dipole moment going this way. Here's another one going in the opposite way. They cancel each other out. Same thing here. This one is canceled out by this guy. Okay. This one is canceled out by this guy. So the symmetry cancels out the net dipole moments. Right? Therefore, it's going to be a non-polar molecule. Here's another one, just like carbon dioxide, acetylene. Okay. So you have net dipole moments going towards the carbons. What do you guys think? Dimethyl ether, is it polar or non-polar? I'll give you 30 seconds. Okay, dimethyl ether. Okay, who says dimethyl ether is non-polar? Who says dimethyl ether is polar? Yeah, thank you. It is a polar molecule. Why? You can see that your partial negative charges are like red means partial negative. Nathan just pointed out hexafluorobenzene heat map is really off, but it's okay. So red means higher electron density, meaning partially negative. Blue means partially positive. So there's a clear charge separation in the molecule, like blue region and the red region. Therefore, that's a polar molecule. Okay? If this was a non-polar molecule, then we should have seen a red region here as well. That would have been symmetric. Okay? We don't have that here. Therefore, it's going to be a polar molecule. Okay? Because the charges are not symmetrically distributed. All right. Any questions, concerns, comments at this point? The point is, okay, we can look at the symmetrical distribution of the charges and determine whether a molecule is polar or non-polar. Okay, that's the point there. Now, let's try to do that with these guys. Let's see. All right. We have close to, actually, we have more than 90% responses now. Okay, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And okay, I know it seems like, we have selected all of them, but I see that this has a higher, density, and this, which are the correct answers. Okay. So here, like, let me draw the dipole moment. So you have two dipole moments going in this way and this way, they cancel each other out. And the same thing here, we did this already. They are canceling each other out. And here we have 1, 2, 3, 1, 2, 3. If you want to do the head to tail, here's my 1. Okay. And here's my 2. And here's my 3. Okay. So they cancel each other out. These are non-polar. On the other hand, the first molecule over here, these two cancel each other out. Okay, but this doesn't, right? This has a dipole moment going in this direction. And here we have something going in this direction. And here we have something going on in this direction. So they have net dipole moments. That's why these three are the correct answers for this question. 73% of us selected them, which is good. Any questions, concerns, comments? This is how we can use the symmetry to determine the polarity of the molecule without, drawing the dipole moment, bond dipole moments. All right, one last question, one for the road. Let's try this. Here we go. Right away. A and B, right? Because we know nitrogen is the most electronegative atom, that is partially negative. The arrowhead of my net dipole moment must go towards nitrogen. In this case, the arrow tail is near the nitrogen, therefore those two are out. Okay? Between C and D, we know nitrogen is partially negative, my hydrogens are partially positive. Okay? So my arrowhead is fine. You can see the arrow tail is in between my 3 partially positive atoms. Okay. Therefore, this is beautiful. This is beautiful. I like that. The problem with option D is it is just showing us the bond dipole moment for the carbon nitrogen bond, not the net dipole moment. Okay. This is not drawing, because this is not showing the net dipole moment. Option D is incorrect as well. I would go with option C as my answer for the net dipole moment for that part. All right, with that, here's the attendance code.